My name is David Dempsey, and I'm delighted to present some recent work with my co-workers Shane Cronin, Samuel May, and Andreas Campolia at the University of Auckland. And we have been looking at forecasting models for volcanic eruptions at Whakaari in New Zealand. And this was really motivated by a fatal eruption that occurred late last year. And we took a look at some of the data and saw some unusual signals in the build-up to eruptions that led us to believe that perhaps some short-term forecasting would be possible and might actually be helpful at a site like this. So for some background, this wasn't all over the news at the time. The Whakaari is a very popular tourist volcano in New Zealand. It's here in the offshore Bay of Plenty. It's a submarine volcano, but the cone does poke above the water. And so it's very popular with tourists. There are boats that come across. People walk up to the vents, have a look around, and then return. Helicopters will visit the island as well. Over the last 10 years, there have been 5 eruptions. And unfortunately, tragically, last year, the 5th eruption occurred shortly after a tour group had been up at the vents here. The surge traveled down this valley and ended up killing 21 of the guides and tourists. In New Zealand, we operate a volcano alert level system to help understand the hazard at our different volcanoes. This ranges from 0 up to 5, depending on the level of hazard present. Whakaari, prior to the eruption, was at a volcano alert level of 2, which is the highest level you can attain before a volcanic eruption is in effect. And this alert level is set by an expert consensus process where you have monitoring scientists who are very experienced with the volcano, looking at the data, routinely consulting with each other and deciding what an appropriate level is. However, this alert level system could be complemented with some real-time forecasting tools that take a different view of the data and just provide additional perspective on what the likelihood of a future eruption is. So we have looked at 9 years of data at Whakaari. In particular, we have been looking at a seismometer that's located about 1 kilometre from the main vent. And what we do with that data is process it to look in particular between 2 and 5 hertz, which at Whakaari is known to be particularly informative about the volcano state. So this is often called a volcanic tremor. In that time, as I said, we had 5 eruptions, and they are each coloured differently here, with 1 month shaded either side. During that time, there have been a few periods of unrest, for example, in early 2013, late in 2015, and again prior to the 2019 eruption. However, they don't always culminate in an eruption. We have also been looking at precursors, or signals that occur prior to some of these eruptions, and that's the focus of this presentation. To analyze these precursors, we took a machine learning approach based on time series feature engineering. And what we would do is take the data, we would chop it into short windows, and for each of those windows, we would extract 700 features from the time series. So an example of the feature is just the average value of a time series. It's just something that tells you a little bit about this short section of data. Other examples include the maximum value in a time series, or the number of peaks that have occurred. We can also look at the gradient of linear regressors, or we can look at Fourier coefficients, which are essentially just the best fitting sine or cosine functions at different frequencies, and these have been particularly important. We can also look in the total energy of the signal, and that as well is quite informative of the volcano state. So in addition to looking at these features, we're very interested in how they change over time. And we'll do that by taking a window of data and sliding that window along. So if you think, for example, the 4-hour Fourier coefficient, which is just a 4-hour oscillating sinusoid that we're fitting to the data. Then as I slide our window along, we'll end up finding a better fitting or a best fitting sinusoid that will have a larger or smaller amplitude, depending on what part of the data I'm looking at with the window. And if I look at that over time, I'll find that the feature value changes. Sometimes it has small values, sometimes it has large values, but I'm particularly interested when it has anomalous values prior to eruptions. And we can think a little bit more about what anomalous means from a statistical sense. So taking again the example of the 4-hour Fourier coefficient, we have found that these are sensitive to strong 4-hour bursts of seismicity or tremor. So bursts that are about 4 hours in duration. Now, if I look at the 4-hour Fourier coefficient over 9 years, it seems to have this nice little distribution. Sometimes it's small and sometimes it's large. If we only look at the values of that 4-hour Fourier coefficient in the 48 hours prior to an eruption, we tend to get some very large values. So each of the colors here corresponds to a different eruption of the 5 that we've had in our study. And we can do a statistical test to say, well, how likely is it we just randomly selected these values from the overall distribution in those 48 hours leading up to eruptions? And what you conclude is that it's exceedingly unlikely that we might have just randomly got those values. The p-value is very, very low, even accounting for the fact that we're doing a lot of these statistical tests. So that tells us that there is something anomalous about the 4-hour Fourier coefficient. We can use that as the basis of a sliding window and checking how it evolves over time. So this little video is just showing as we slide a window from right to left over about 2 days worth of data. This is the signal that we're analyzing down the bottom, and the blue line is the feature and how the feature is evolving over time. On the vertical axis here, I've got a z-score that's essentially showing how different that feature is from an average value across the entire time series. And what we're finding is as it slides across this feature in particular, it spikes up to a very large value, 2 standard deviations away from the mean. This tells us that we're in unusual territory. In this case, it happened about 16 hours before the eruption occurred. And what we think is happening here is gas coming off a shallow parcel of magma, working its way upwards into the shallow groundwater system, and over time leading to heating and pressurization that later leads to an eruption or a steam explosion. And that process takes about 16 hours from when the degassing occurs here. Now, I showed you that with the 4-hour Fourier coefficient. We've actually looked at lots and lots of these features, picked out the most important ones, and combined them together in a model called a random forest. And the random forest has been trained to make a decision about whether or not it thinks an eruption is likely in the immediate future, 48 hours, based on a combination of features it has seen in the last 48 hours. Here's roughly how that model looks like over time. So the output itself is in purple and it can be interpreted as a kind of a degree of concern or suspicion by the model of a future eruption. And it does require that we set a threshold at which we think it's appropriate to trigger an alert. In this case, we've set a threshold here, and that's based on our analysis of previous eruptions of thresholds that would trigger alerts. In this case, you're looking at an alert that would be issued about 16 or 17 hours in advance of this eruption here. Now, we've gone through a very rigorous process of cross-validation, and the reason for that is to avoid an overfitted model that doesn't perform very well in the future. And we do cross-validation by, we have 5 eruptions in our data set. So what we'll do is we'll take one of those and leave it out. From the rest of the data, we will select what we think are the important features or the important precursors, and we will train a model on just those data. And then we'll ask it what its opinion is of this eruption that we have withheld at the beginning. So here is an example. There was an eruption in 2012. We trained a model only on data from 2013 to 2019. It did a number of things. For a start, it issued 18 hours of warning of this eruption here, which was a good sign that it's detecting real precursors and responding to those. It did, however, issue a false alarm earlier on. False alarms are something I will touch on very soon. Here's another example. This was an eruption in 2013, again excluded from the training data now. But when tested, the model was able to issue 75 hours alert, or about 3 days warning. A second eruptive episode in 2013. This was actually a sequence of 3 eruptions over 5 or 6 days. Here we were able to capture 2 of those eruptions, but we missed the middle one. There was another eruption again in 2016. This one appears to have been quite different to the other eruptions because there is very little suspicion at all early on of any kind of eruption precursor. So it's entirely missed by a forecaster not trained on that data. And then finally, the fatal eruption in 2019. As I mentioned earlier, there was a 4-hour burst that occurred about 16 hours before that, and so that's what triggered our forecaster early on. So one of the things we've learned with this forecaster and talking to some of the people who may end up using it is that the communication of these alerts is really important and essential. So for example, these statements below are all correct. Our forecaster, for instance, when we run it over all the data, ends up issuing 11 false alerts for every true alert that it was able to capture. And it was able to capture 4 out of 5 of those eruptive periods, but it did it at the cost of about 50 false alerts, if you like. However, another way of phrasing that is saying, well, if an alert is issued, there is now a 1 in 12 chance for an eruption to occur in the near term, which might be the next 5 days or so. That tends to be the average length of our alert periods. Or another way of thinking about it is that Whakaari would only be under alert for about 2 or 3 days on average every month if a system like this was adopted and had been operating over the last 9 years. So depending on the way in which it's presented, the forecaster can appear more or less effective. And that's one thing we found to be quite important when talking about its outputs. Now, of course, this is just a hindsight study, notwithstanding that we're doing cross-validation to try and emulate true forecasting. But the real test only comes with forward operation of the model, and we have been doing that since February this year. In that time, our forecaster has issued 2 alerts. Both of those appear to have been triggered by regional earthquakes that have occurred a long way away from the volcano. Here's an example. The largest was a magnitude 5.3. This occurred in August. So one of the things we're working on right now is how to scrub out those regional earthquakes from the incoming data stream so that they don't end up triggering alerts, and whether doing so improves the specificity of our model. So if I can wrap it up, at Whakaari we think there is very clear evidence of eruption precursors. These are statistically significant. They do occur hours to days before eruptions, so we think that gives lots of time for evacuation and a real-time forecaster to actually provide useful information. And so the future work will be on how best this can be integrated with the existing systems, who has access to these kinds of alerts and makes decisions with regard to access to the volcano, and whether or not similar systems can be developed at other volcanoes in New Zealand or around the world. So thank you very much for watching, and you can find many more details of this study in our paper published earlier this year.